NEC 110.10 mandates that conductors must be protected against overcurrent using circuit breakers or fuses. However, the time it takes for a circuit breaker to trip might exceed the time needed for a fault current to damage the wire's insulation. Conductors possess specific fault current ratings. For instance, number 12 THHN wire has a fault current rating of 2768 amps for a single cycle. Should a fault current equal to or exceeding this value flow through the wire for one cycle, the insulation could sustain damage. Circuit breaker tripping times are measured in cycles. The tripping time for most circuit breakers typically ranges from 1 to 2 cycles, translating to approximately 0.16 to 0.32 seconds. While circuit breaker manufacturers' representatives might assert that the wire is adequately protected because the circuit breaker complies with UL 489 standards, it's crucial to understand that UL 489 primarily addresses the circuit breaker's performance and not the safeguarding of downstream conductors. It is indeed accurate to state that a fault occurring on the load side of the circuit breaker could potentially permit enough fault current to pass through the number 12 wire to compromise its insulation. There are several ways to resolve this. Firstly, one can consider increasing the wire size. Secondly, using number 10 wire, which boasts a fault current rating of 5010 amps for one cycle, offers enhanced protection. Thirdly, employing a faster tripping circuit breaker can mitigate the risk. Fourthly, installing a circuit breaker with a tripping time of less than one cycle can provide quicker fault interruption. Fifthly, implementing a current-limiting fuse in conjunction with the circuit breaker serves as an additional safety measure, because a current-limiting fuse will interrupt the fault current more quickly than a circuit breaker. It's worth emphasizing that the National Electrical Code, or NEC, prioritizes the utilization of the most effective method to ensure thorough overcurrent protection. In many scenarios, increasing the wire size represents the most practical and reliable solution. To further understand the implications of exceeding a conductor's fault current rating and the protective measures outlined in NEC 110.10, it's essential to delve deeper into the characteristics of fault currents, the construction of circuit breakers, and the nuances of electrical safety standards. Fault currents, unlike normal operating currents, are characterized by their high magnitude and rapid rise time. They typically arise from insulation failures, short circuits, or ground faults within an electrical system. When a fault occurs, the sudden surge of current can generate intense heat within the conductor, potentially leading to insulation melting, arcing, and even fire hazards. The extent of damage depends on several factors, including the magnitude and duration of the fault current, the conductor's material and size, and the ambient temperature. Circuit breakers are designed to interrupt fault currents and protect downstream equipment from damage. They operate by sensing an overcurrent condition and tripping a mechanical mechanism that opens the circuit. The tripping time of a circuit breaker is a critical parameter that determines its ability to limit the duration of the fault current. Faster tripping times are generally desirable as they minimize the thermal stress on conductors and equipment. However, achieving faster tripping times can be challenging due to the inherent inertia of the mechanical components within the circuit breaker. UL 489 is a widely recognized safety standard that specifies the performance requirements for molded case circuit breakers. It outlines various tests and criteria to ensure that circuit breakers can safely interrupt fault currents and protect against overloads. However, UL 489 primarily focuses on the circuit breaker's ability to withstand fault currents without failing itself. It does not explicitly address the protection of downstream conductors from insulation damage. This is where NEC 110.10 comes into play, as it mandates that conductors be protected against overcurrent in accordance with their ampacity and fault current ratings. In addition to increasing the wire size or using faster tripping circuit breakers, current-limiting fuses offer an effective means of mitigating fault current hazards. Current-limiting fuses are specially designed to interrupt fault currents within a fraction of a cycle, significantly reducing the thermal stress on conductors and equipment. They achieve this by incorporating a fusible element that rapidly melts and vaporizes when subjected to high fault currents. The resulting arc is then quenched by a special filler material within the fuse body. Current-limiting fuses are particularly useful in applications where high fault currents are anticipated or where sensitive electronic equipment needs to be protected. When selecting overcurrent protection devices, it's important to consider the specific characteristics of the electrical system and the potential fault currents that may occur. A thorough short-circuit study can help determine the available fault current at various points in the system. This information is essential for selecting circuit breakers or fuses with adequate interrupting ratings. It's also crucial to coordinate the overcurrent protection devices to ensure that the device closest to the fault will trip first, minimizing the impact on the rest of the system. In addition to NEC 110.10, other relevant sections of the National Electrical Code address conductor protection and overcurrent protection. For example, NEC 240.4 specifies the requirements for protecting conductors against overcurrent in accordance with their ampacity. NEC 250 provides guidelines for grounding and bonding electrical systems to minimize the risk of electric shock and fault currents. It is important to remember that electrical codes and standards are constantly evolving to reflect new technologies and safety concerns. Staying up to date with the latest revisions of the NEC and other relevant standards is essential for ensuring the safety and reliability of electrical systems. Furthermore, consulting with qualified electrical engineers and inspectors can help ensure that electrical installations comply with all applicable codes and standards. In summary, understanding NEC 110.10 and its implications for wire fault current protection is crucial for electrical safety. While standard circuit breakers may not always provide adequate protection against insulation damage during faults, various solutions are available, including increasing the wire size, using faster tripping circuit breakers, and installing current-limiting fuses. By carefully considering the characteristics of the electrical system and selecting appropriate overcurrent protection devices, it is possible to minimize the risk of fire hazards and equipment damage caused by fault currents. Let's explore the practical implications of these concepts with examples. Imagine a scenario where a 480-volt motor is fed by number 12 THHN wire protected by a 20-amp circuit breaker. The available fault current at the motor is determined to be 10,000 amps based on a short-circuit study. According to NEC 110.10, the number 12 THHN wire must be protected against this fault current. As previously mentioned, number 12 THHN wire has a fault current rating of 2768 amps for one cycle. Since the available fault current of 10,000 amps far exceeds this rating, the number 12 THHN wire is not adequately protected. In this case, one option would be to increase the wire size to number 10 THHN, which has a fault current rating of 5010 amps for one cycle. While this provides some improvement, the available fault current still exceeds the wire's rating. A more effective solution would be to use number 8 THHN wire, which has a fault current rating of approximately 8000 amps for one cycle or even larger. Alternatively, a current-limiting fuse could be installed in series with a 20-amp circuit breaker. A properly sized current-limiting fuse would interrupt the fault current within a fraction of a cycle, limiting the amount of energy that reaches the number 12 THHN wire and preventing insulation damage. Another approach would be to use a faster tripping circuit breaker, such as an instantaneous trip breaker or a high-speed circuit breaker. These breakers are designed to trip very quickly in response to high fault currents, typically within a few milliseconds. However, it's important to ensure that the faster tripping breaker is properly coordinated with other overcurrent protection devices in the system to avoid nuisance tripping during normal operating conditions. In addition to these technical considerations, it's also important to be aware of the potential legal and insurance implications of failing to comply with NEC 110.10. Electrical inspectors are responsible for enforcing the National Electrical Code and ensuring that electrical installations are safe and compliant. Failure to comply with the NEC can result in fines, penalties, and even legal liability in the event of an accident or fire. Insurance companies may also deny coverage for damages caused by electrical systems that are not properly protected. Therefore, it's crucial to prioritize electrical safety and ensure that all electrical installations are designed and installed in accordance with the latest edition of the National Electrical Code. Remember to consult with qualified electrical professionals for guidance on specific applications and to ensure compliance with all applicable codes and standards. Now let's delve into a slightly more complex scenario involving a panel board with multiple branch circuits. Suppose a 480-volt panel board has a main breaker rated for 100 amps and several branch circuits protected by 20 amp circuit breakers. Each branch circuit feeds various loads such as lighting fixtures, receptacles, and small motors. The available fault current at the panel board is determined to be 20,000 amps. In this situation, it's important to consider the fault current ratings of all conductors within the panel board, including the main feeder conductors and the branch circuit conductors. The main feeder conductors, which connect the panel board to the upstream power source, must be sized to handle the available fault current without sustaining damage. Similarly, the branch circuit conductors must be protected against fault currents in accordance with NEC 110.10. If the branch circuit conductors are number 12 THHN wire, as in the previous example, they may not be adequately protected against the available fault current. In this case, several options are available. Firstly, the branch circuit conductors could be upsized to number 10 or number 8 THHN wire to increase their fault current ratings. Secondly, current limiting fuses could be installed in series with the branch circuit breakers to limit the amount of fault current that reaches the conductors. Thirdly, faster tripping circuit breakers could be used to minimize the duration of the fault current. In addition to these measures, it's also important to ensure that the panel board itself is adequately rated for the available fault current. Panel boards are typically marked with a short circuit current rating, which indicates the maximum fault current that the panel board can safely withstand. If the available fault current exceeds the panel board's rating, the panel board may need to be replaced with a higher rated unit. Furthermore, it's important to consider the coordination of overcurrent protection devices within the panel board. The main breaker should be coordinated with the branch circuit breakers to ensure that the branch breaker closest to the fault will trip first, minimizing the impact on the rest of the system. Coordination studies can be performed to determine the appropriate settings for the overcurrent protection devices to achieve optimal coordination. In summary, protecting conductors against fault currents in panel boards requires a comprehensive approach that considers the fault current ratings of all conductors, the interrupting ratings of overcurrent protection devices, and the coordination of protection devices. By carefully evaluating these factors and implementing appropriate protective measures, it is possible to minimize the risk of electrical hazards and ensure the safety and reliability of the electrical system. Before we conclude, let's discuss the importance of proper installation and maintenance of electrical systems. Even if an electrical system is designed in accordance with all applicable codes and standards, it's still crucial to ensure that it is installed correctly and maintained properly. A proper installation can compromise the safety and performance of the electrical system, potentially leading to hazards such as electrical shocks, fires, and equipment damage. Similarly, inadequate maintenance can cause electrical components to deteriorate over time, increasing the risk of failures and hazards. Therefore, it's essential to use qualified electrical contractors for all electrical installations and to establish a regular maintenance program to inspect and test electrical equipment. During installation, it's important to ensure that all conductors are properly sized, insulated, and terminated. Conductors should be installed in accordance with the manufacturer's instructions and all applicable codes and standards. Connections should be tight and secure to prevent overheating and arcing. Grounding and bonding connections should be properly installed to minimize the risk of electric shock. During maintenance, electrical equipment should be visually inspected for signs of damage or deterioration. Connections should be checked for tightness and corrosion. Insulation resistance should be tested to ensure that conductors are properly insulated. Overcurrent protection devices should be tested to verify that they are operating correctly. Any damaged or worn component should be replaced promptly. In addition to these routine maintenance tasks, it's also important to perform periodic thermographic surveys to identify hot spots in electrical equipment. Thermography uses infrared cameras to detect temperature differences in electrical components, which can indicate loose connections, overloaded circuits, or other potential problems. By identifying these problems early, it is possible to prevent equipment failures and electrical hazards. In conclusion, protecting conductors against fault currents requires a multifaceted approach that encompasses proper design, installation, and maintenance. By understanding the principles of NEC 110.10, selecting appropriate overcurrent protection devices, and implementing a comprehensive maintenance program, it is possible to create safe and reliable electrical systems that protect people and property from the hazards of fault currents.